Right. Okay. So in this lesson, we are like, this is part of lesson 4 on study 2D study diffusion equation. Okay. So in this, we are going to look like implement the calculation of element stiffness matrix and element force vector for the 4 noded element. Okay. For the 2D diffusion equation. We have seen the pseudocode. Okay. Now, before we solve these problems, okay, so let us see how to calculate the element stiffness matrix for an individual element. Let us say this is our element. Okay, these are the coordinates. Okay, so like in physical domain, like when we generate the mesh, okay, let us say we have some arbitrary like 10 or 1000 or 100,000 million elements. Okay, so this is one of our element. And for this element, we want to calculate the element stiffness matrix of the force vector. Okay. So the node numbers are 11, 21, 53, 44. Okay. These are arbitrary numbers as I assigned. And what's important is the coordinates. Okay. These are the coordinates. And this is a like axis aligned element. Okay. But as you are going to see, the beauty of the finite element method is it doesn't matter how the element is aligned, whether it is aligned with the coordinates or not, it doesn't matter. Okay, we can easily change the coordinates here, and we can have an arbitrary like non-axis aligned element, and we can still use the same subroutine for calculating the element stiffness matrix and force vector. Okay, so for some verification, so we have the area of the element. Okay, so in the x-axis the length is 0.1 and on the y-axis the length is 0.07. So the area is 0.1 multiplied by 0.07. So 0.007 square units. Okay, it would be meters, it would be millimeter, doesn't matter. So okay, at this point what we need is are the numbers. Okay. Okay. So and I said we are going to use 4 draft points. Okay, these are the coordinates and the weight for each point is 1. So what I have done is, so I have like just quoted this. Okay, so we are assuming that the mu, that is the diffusion coefficient, is 1. Okay, it could be anything, we can change later. And these are our x1 y1 x2 y2 x3 y3 x4 y4. These are our nodal coordinates. And remember, we have to order them in the counterclockwise direction, because that is how we store the basis functions. Okay, we store the basis function of the nodes in the counterclockwise direction, so the node should be in the corresponding order. So that is 11, 21, 53, 44, and there is coordinates. So x1 y1, x2 y2, x3 y3, x4 y4. Okay, so that's how I have ordered them. And we have 4 draft points. So NGP is 4, and GPT is 1 is for the xy coordinate. Okay, this is the xy coordinate, and GPT is 2 is the eta coordinate, and GWTS is the weights, draft point weights. Okay, so we first initialize. Okay, so let's say K lateral. This is our element stiffness matrix, that is lateral stiffness matrix. Okay, so should be of size 4 by 4. Okay, we have 4 nodes, each node has 1 degrees of freedom, so 4 by 4. And F lateral, this is our element force vector. Okay, 4 comma 1. We have to initialize them to 0 so that we can keep on adding within the for loop corresponding to the draft points. Okay, so we create a loop over draft points. So 1 to NGP. Okay, so that loop ends here. Okay, and then so first what we need, okay, so we go back to this pseudocode. Okay, first we need to get the local coordinates for xy eta, and then what is the weight. Okay, so first we get the coordinates. Okay, so this is stored in GPTs 1. Okay, for the current loop counter GP, we get the corresponding xi and the corresponding eta. Similarly, we get the corresponding weight. Okay, here I am using WT for weight. Okay, so like an abbreviation instead of omega. Okay, so first we have the coordinates of xi eta and we have the weight. Next, we calculate the basis functions. Okay, so basis functions n. Okay, so okay, we have 4. Okay, we can directly calculate them. Now let's go back to this. Okay, so these are our basis functions. Okay, so 0.45, sorry, 0.25. 1 by 4 is 0.25. So I am using the value directly. 1 minus xi, okay, multiplied by 1 minus eta. Okay, this is our first basis function. And how do we store them? We store them as row matrix. Okay, so comma 0.25 1 plus xi multiplied by 1 minus eta, comma 0.25 1 plus xi multiplied by 1 plus eta, comma 0.25 1 minus xi multiplied by 1 plus eta. Okay, so then we close the square bracket. Okay, so here we have our basis function matrix n. Similarly, we calculate the derivatives of basis function. Okay, dn by dxi. Okay, this is minus 0.25 multiplied by 1 minus eta, 0.25 multiplied by 1 minus eta, 0.25 multiplied by 1 plus eta, 0.25 multiplied by 1 plus eta. Okay, so watch out for any errors, any mistakes. And then dn d eta, okay, just for alignment. Okay, minus 0.25 multiplied by 1 minus xi. Okay, minus 0.25 multiplied by 1 plus xi. 0.25 multiplied by 1 plus xi. 0.25 multiplied by 1 minus xi. Okay, close the bracket. Okay, so if you want, you can also take care of the alignment. Okay, now after we calculate the derivatives of the basis functions, we calculate the Jacobian. To calculate the Jacobian, we need dou x by dou xi, dou y by dou xi, dou x by dou eta, dou y by dou zeta. And how do we calculate them? We evaluate this summation of these products. Okay, let us create a Jacobian matrix. Okay, let's call it Jac. Okay, it has size 2 by 2. Okay, so the first entry is, okay, this is dx by dxi. Okay, I'm using d instead of dou just to make it simple. Okay, so how do we calculate this? Okay, so sum of products of this dou n by dou xi xi. Okay, so dou n dn by dou n by dou xi. Okay, the first one multiplied by x1 plus dn by dxi, the second basis function derivative multiplied by x2 and so on. Okay, so the third basis function derivative multiplied by h3, fourth basis function derivative multiplied by h4. Okay, similarly, we can evaluate this, okay, 2 comma 1. So here the derivative is with respect to eta. Okay, 2 comma 1. Okay, so just to avoid making mistake, dn by d eta multiplied by x1, dn by d eta for the second basis function multiplied by x2, dn by d eta for the third basis function multiplied by x3, plus dn by d eta for the fourth basis function multiplied by h4. Okay, this is entry 2 comma 1. Okay, so we often made mistake and we swap 1 comma 2 and 2 comma 1 because this is not a symmetric matrix. It is very important that we maintain the order. Okay, now j1 comma 2, so this is that is dou y by dou z. So what we can do, so we need dou y by dou z, we copy this. Okay, so instead of x we need y coordinates. So y1, y2, y3, y4. Okay, and then okay, dou y by dou eta, so that is Jacobian 2 comma 2. So this is Jac. Okay, so here we need y coordinates. Okay, so this is our Jacobian matrix. Once we have this, we can calculate its determinant and we can calculate its inverse. Okay, so now we are at this point. Next, we calculate the derivatives of the basis function with respect to physical coordinate, that is dou n by dou x and dou n by dou y. Okay, so what we need dn by dx. We have 4 basis functions, so we have 4 comma 1 and dn by dy again 4 comma 1, 4 comma 1 or 1 comma 4. Okay, 1 comma 4. We want a row matrix. Okay, so what we do, what we need, dou n by dou x, the first one is Jac inverse 1 comma 1 dou n by dou xi 1 plus Jacobian inverse multiplied by 1 comma 2 dou n by dou eta 1. Okay, so to calculate the derivative of the basis function with x, we multiply the inverse of the Jacobian with this. So for I equal to 1, so the inverse 1 1 dou n by dou xi and 1 comma 2 dou n by dou ni by dou eta. Okay, that's what we are doing. Okay, dou n here I equal to 1. Okay, so we are taking the dou n by dou xi for the first basis function and dou n by dou eta for the first basis function. Similarly, we calculate dn by dy for the first basis function. Okay, so Jac inverse, this would be the second row and multiplied by the derivative with respect to xi. Okay, again, like we are in the second row, so we get the second component of the second column of the second row and then derivative with respect to eta for the first basis function. Okay, so now we have to repeat this for all the other basis functions. So the easiest way is to create a for loop for I equal to 1 to 4. So we place them in the inside the for loop. Okay, here our loop variable is this. Okay, I, 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 I. Okay, so in this way we calculate the derivatives of the basis functions with respect to x and y for all the basis functions. Okay, we have 4 basis functions, so I equal to 1 to 4. If you have like different element with different number of basis functions, this for loop remains exactly the same. Okay, now we have the derivatives here, and then we can create our G matrix. Okay, so G is 2 by 4 matrix. Okay, or we can create directly. Okay, the first one is dn by dx, comma dn by dx of 2, dn dx of 3, and dx of 4. This is our first row. Okay, this is our first row. And then our second row in terms of d and dy. Okay, that's our G matrix. Okay, we already have our N matrix. Now, next we do this step. We create and add to the stiffness matrix. Okay, so K lateral. So remember, we need to add to the existing value. Okay, so K lateral equal to K lateral plus mu, our diffusion coefficient, multiplied by G transpose, multiplied by G, sorry, then multiplied by the determinant of the Jacobian, and then multiplied by the weight. Okay, so mu G transpose G, J multiplied by weight. Okay, mu G transpose G, J is determinant of J multiplied by weight. Similarly, F lateral, so we need to add to the previous one. Okay, N transpose, okay, what we have here, N transpose F, N transpose multiplied by F, determinant of J multiplied by weight. Okay, so here we need F. Okay, we can say F equal to 2. Okay, just for evaluating the matrices and vectors. Okay, so that's all. Okay, that is how we calculate the element stiffness matrix and element force vector for a 4-noded element for the 2D diffusion equation. Okay, so again, so first we get the material properties, that's and the source term. Okay, then we have the x and y coordinates corresponding to all the nodes. Okay, and then we have the number of number of gross points, how many gross points we want to use, and the corresponding coordinates and weights. Okay, before we loop over the gross points, we initialize the stiffness matrix and force vector to zeros so that we can keep on adding to them. Okay, and then we loop over the gross point, we get the coordinates of the xi and eta, that is our lateral coordinates, and the weight of the corresponding gross point. We calculate the basis functions at these coordinate values, and we also calculate the derivatives of the basis functions at the coordinate value. Then we create the Jacobian matrix by taking the products of the derivatives of the basis function with lateral coordinates with x and y coordinates of the nodes. Once we have the Jacobian matrix, we can calculate its determinant, we can compute its inverse, and then finally we can calculate the derivatives of the basis function with respect to physical coordinates x and y. And once we have all the all the basis functions and their derivatives. We can create our G matrix. Okay, we don't need this. Once we know G, we can calculate the element stiffness matrix on the corresponding Ross point and then add it to the previous contribution. Similarly for the force. Okay, now let us run this. Okay, I'm going to change the dictionary. Right, okay. So these are some, okay, dn by data. Okay, so that is, yeah, dn by data. No, we're not printing anything. Okay, so let us print K lateral and F lateral. Okay, so this is our stiffness matrix and this is our force vector. So at this point we are not going to verify its correctness, but there are some checks that we can make. Okay, some sanitary checks. The stiffness matrix should be symmetric. Check if it is symmetric. Okay, and the force vector, the contribution should be equally distributed to all the 4 nodes. Okay, so all the 4 nodes are the same. See, these are just some sanitary checks to make sure we are getting at least some correct results. Okay, we are not verifying this. Okay, but these are some sanitary checks to make sure that we are in the right path. If the stiffness matrix is not symmetric, then you made a mistake. If the contribution to the force vector is not equally distributed, like they are not the same, then there is a mistake. So these are some ways to check and debug your code. There is also another check that we can do. Okay, we know the area of the element, it should be 0.007, and we saw that the Jacobian, the determinant of the Jacobian tells us the area change. So like if you do the calculation, it tells us the area of the element as well. Okay, what do I mean? Okay, area is 0.0. Okay, we calculate the area. So what we do? Okay, once we calculate the determinant of Jacobian, now okay, let us go back to, yeah, let us come here. Now here our stiffness matrix is this, and we are using Gauss points to evaluate the stiffness matrix. Now what happens if this quantity is 1? If this bracket, instead of this bracket we have 1. Okay, so when we have 1, that what are we doing? So when we have 1 here, we are simply evaluating the integral. Okay, there is no function, we are evaluating the integral. So integral of this domain is area. Okay, so if we have 1 here, so if you add this contribution of from all the Gauss points, we should get the area of the element. Okay, that is, after calculating the determinant of Jacobian, we can calculate the area like this, J multiplied by the weight. Okay, that is, instead of this mu G transpose G, we have just determinant of J and omega, that is weight. Okay, that should give us the area. Again, don't forget to add to the previous because we are looping over Gauss points. Okay, so let us print the area. So let us run this. Okay, what is the area? Area is 0.7 into 10 power minus 3, that is 0.007. And what do we have for this? 0.007. Okay, so we got our calculations are correct. Okay, so I'm not expecting any bugs in this code. Okay, that we will verify eventually when we solve the problem. But okay, so this is how we calculate element stiffness matrices for any problem using finite element method. Okay, now what we need is we prepare the arrays, we prepare the coordinates, we prepare the Gauss point coordinates, and then we loop over the Gauss points. Okay, at each Gauss point we get the coordinates of our local coordinate, like the values of our local coordinate xi and eta, and we also need the weights. Okay, so once we have the values of the coordinates, we calculate the basis functions, we calculate their derivatives, that is the derivatives of basis functions with respect to local coordinates, and then we prepare the Jacobian matrix. Okay, and then we calculate the determinant of the Jacobian and its inverse. Once we do that, we can calculate the derivatives of the basis function with the global coordinates x and y. Once we have the derivatives of the basis function with the global coordinates, we prepare our gradient matrices. So in this case, we have G, gradient displacement matrix, and if we solve elasticity problem, we have our B matrix, which we can prepare using these derivatives. Okay, and then our stiffness matrix would be the same, B transpose dB J multiplied by weight. Okay, so this procedure is the same. This is how we do. In the next part, I'm going to show you how to integrate this, like we convert this into a function and then solve some examples.